Okay, I think now everybody should be here, and I welcome everybody to this webinar about the circular layout. My name is Benjamin Niedermann. I'm an algorithms engineer of yWorks and a member of the layout algorithms team. So this basically means that I daily work on layout algorithms that you can use to visualize your connected data. But apart from that, I also give this series of webinars where I would like to introduce you to the different layouts offered by the yFiles library, so the main product of yWorks. And in this series, I would like to answer questions like when to use these layouts and how to use the layouts. And I always also give some coding examples, but I also present use cases to give you ideas when you could use these layouts for your data. And today I would like to introduce you to the circular layout. And in this image, you already can see the main idea of the circular layout, namely that the nodes are placed on circles and these circles are then connected by some kind of backbone, which has a tree-like structure. And in the same scope of the webinar, I also would like to introduce the balloon layout, which is a layout and standalone layout of the yFiles library that you can use to visualize, for example, tree structures. And the balloon layout does this also in a circular fashion by placing the nodes around the root nodes on circles. And I will also present in this episode the close connection between the circular layout and the balloon layout, namely that the balloon layout is used as a subcomponent of the circular layout. Before I get into the details, I first would like to clarify what I actually mean with the circular layout, and then I also want to present some use cases, and after that we get more into the details about the circular layout and the balloon layout. So let's start with the question, what is the circular layout? And obviously the main property is that the nodes are arranged on circles and also on stars. And these circles are then placed such that they are connected by some kind of backbone structure, and this gives you also a typical layout, or this is a typical characteristic of these circular layouts. So basically what you get is an emphasis on clusters and tree structures expressed by these circles, which are then connected by this backbone. And in order to also reduce the clutter of the edges, when you have a lot of edges, for example, you can also use techniques like edge bundling to introduce a visualization technique that helps you to reduce this clutter of information. And in the following, I would like to introduce you to three use cases. The first use case is our social networks. Here, the idea is, for example, in this image that you have one big cluster of members that have a lot of connections, and then there are some satellite nodes attached to this big cluster, such that they have either just a star-like structure or a tree-like structure attached to this cluster. And again, in order to reduce the visual clutter of these many edges, we have introduced here the edge bundling technique, which basically means that the edges are bundled together and form one path until they split up again, going to their own nodes. Second use case are computer networks. Here you often have some kind of basic backbone structure, which is also often tree-like, but of course you can also have more complex structures. And this backbone structure connects subnetworks with each other. Here in this case, very simple structures, namely ring topologies, but these structures can be, of course, more complicated. And this gives you a very easy or a very simple way to visualize this computer network. And the third use case that I would like to present comes from computational biology. And here it's about the spread of the bacterium Staphylococcus in a given hospital. And the idea is that the different subtypes of this bacterium are colored using different colors, uses different colors. So here the persons, for example, patients, but also the medical staff, gets the color of the subtype of the bacterium with which they are infected. And then what we also did is that we partitioned these people into clusters representing the wards of the hospital. So this is a information that is contained in the data that we are given here. And the edges then describe the connections between the people. So here, for example, in this ward, you see that there are many connections between the people and there are only few connections going to the other wards of the hospital. And this also gives you a very simple possibility to visualize a really complex network with different clusters and different groups. Later on in the coding example, I will use this example to show you how to configure the circular layout in the yFiles library. So summarizing these three use cases, we can say that if you have data that has a lot of clusters or groups, and these groups are connected by some kind of backbone structure, then you can use the circular layout and to visualize these clusters, but also to visualize the structure connecting these clusters. So summarizing, you get a large emphasis on groups and clusters with a circular layout. So in the reminder of this webinar, I will the reminder of the webinar will be structured as follows. First of all, in the first part, I will talk about the principles. And then after that, I give a short demo on our webpage that you also can access, showing some features of the circular layout. And then in the final part, I also will give some coding example in yFiles HTML. But if you come from another platform like .NET or Java, it's basically you can also easily understand what I will do there because the API is basically the same on all platforms. Maybe at this point, I also should mention that if you have some questions, then please just ask them in the chat. And after this webinar, there will be also a Q&A session where I will answer your questions. In case that you watch this video on YouTube, because this video will be set online on YouTube, then and you have some questions, then just leave the question below the YouTube video and we will try to answer your questions as soon as possible. And yeah, now I would like to start with the first part of this webinar, namely the principles of the circular layout, where I explain the main approach, how the layout is created. And this should give you some idea how to configure also the circular layout. So, and this I would like to explain at a very simple example, namely this graph, and I layouted this with the organic layout that you also find in the yFiles library. And now I would like to explain how the circular layout creates an own layout based on this graph. So it does not take any geometric information, but only the structural information. And the first step is that it identifies the partitions that should be layouted as circles. So for example, these nodes that are marked green will be placed on a circle and the nodes that are marked red are placed on another circle and so on. And the blue edges or the blue nodes are basically the structure in between or and also these edges connecting these partitions. And there are basically two possibilities to configure the circular layout. Namely, either you can decide to find these partitions completely automatically so that you don't need to do anything. In that case, it uses bi-connected components. I will explain what this is in 1 minute. And then the other possibility is that you define your own partition. So you basically can mark these nodes green, red, and orange on your own, and then the algorithms know which nodes should be placed on which circles. So if you want to do this automatically, you can use these kind of bi-connected components, and then it's of course important to know what are bi-connected components. So if you look at a graph, then we say that a graph is connected if between any pair of nodes, there's a path that connects these nodes. So for example, if you look at this node and at this node, there's obviously a path that connects both nodes. Bi-connected means now that when you remove a single node from the graph still remains connected. So in this example here, in the blue example, if I remove this node here, the graph is split into two components. So this means that the blue graph here is not bi-connected. But here the brown graph is bi-connected. I can delete any of these nodes and the graph still remains connected. If I delete two or more nodes, then the graph becomes unconnected. So it's not tri-connected, but it's bi-connected. And the algorithms then finds these subgraphs that are maximal large and are bi-connected. So for example, this green partition here is bi-connected and this red one is also bi-connected. And based on these components, it will decide which of the nodes will be placed on circles. And then there are some small variants that you can also use. You will later see this in the demo. So now we have determined these partitions, and now the question is how can we draw these partitions and also the other structure. And what we do is we divide this into independent subtasks. We solve these subtasks and then we merge the results of these tasks. So the first task is that we need to create layouts for the partitions, and we will do this for each partition independently. The second task is then that we find a layout for the remaining structure. So what we do is that we replace each partition by a single node. And in this case, we get a tree structure, and then we then we find a layout for the remaining structure, and then we combine the layouts for these partitions with a layout for the remaining structure, and we get the overall structure. So let's talk first about the task one, about layouting the partitions. And there's one simple possibility, namely that we just use the single cycle layout algorithms that is also offered as a standalone algorithms by the yFiles library. So what it does, it just uses or it places the nodes, for example, for the green partition on a circle, and it decides for the order of the nodes such that the crossings is such that the number of crossings is minimized between the edges. And this we apply on all partitions, and so then we get a simple layout for our partitions. Indeed, there are some alternatives that you can also apply, not only single cycle layout, but for example, also the compact disk layout, which is also a standalone layout, but you can also use it for the circular layout. Here, the idea is that the nodes are not placed on a single circle, but on the disk in some circles. And of course, if you have a large partition, you can use this to make this layout of this partition more compact. So now we have the layout of these single partitions, and the next question is how can we lay out this remaining structure? And the idea is that we apply the balloon layout. And the balloon layout is a layout algorithm that you can use to visualize trees. And it does it in the following manner, namely that it places the root, for example, at the center, and then it places the children of this root node around the center and so on. And this gives you also a circular perspective on your tree data. In case that there are some non-tree edges, which of course could happen, it will reduce first the graph to a tree, and then it will lay out this tree, and then will add the non-tree edges back to the layout. And then there's also one detail that you should also know is that it increases the size of the nodes to the size of the layouts of the partitions. So we already have computed these partition layouts. So for example, for the red nodes, we already know how large the cycle will be. And then we replace this or we set the size of this node to the size of this partition. And then this layout is basically used by the balloon layout. And this results in this tree layout here. So now we have the results of both tasks. So we have layouted the single cycle or the partitions, and we also have layouted the remaining structure. And now we combine them, and this combining is really simple. We just replace these large nodes here with their actual layouts. And we also optimize the rotation of these layouts, but these are more technical details that you don't need to know. Actually, this whole process is done, of course, automatically, but it's good to know how it works because you can customize certain steps of these of this approach, and then it's good to know how it works also from a high level perspective. And I would like to get more into detail for the balloon layout, because when you also know how the balloon layout works, you also can configure this for your purposes, also customizing the circular layout. So at the as a next step, I would like to show you some details about the balloon layout. So as I already said, the idea is that going from the root, we place the nodes around this root. And so there's one layer of the children nodes, and then the next nodes come, so the children of the children, and so on. And this is done in a circular fashion. But you can configure this in a greater detail, namely you can define wedges. So for example, you can say that the root has a certain wedge, for example, 270 degree, and the remaining graph needs to lie in this wedge. So basically you can also express some kind of orientation with this in the graph. And the same you can do for the children nodes. So you can define wedges for these children's, and the subtrees of these children nodes then need also to lie in these wedges. And so for example, the exact extent of this wedge you can define on your own, or you can also, of course, just use the default values. And this is already the main idea of the balloon layout. And knowing this, you already know how to, for example, customize the balloon layout for the circular layout. So altogether, you have seen the basic ideas of the circular layout and also some details about the balloon layout. And next, I would like to also discuss further features. So when you consider this basic approach, this is, of course, you can just use it, and then we have extended it with many different features. And I would like to present some of the features that are available with the circular layout, but there are many more. And if you want to find out more about this, I refer also to the D-Guide, or also to our homepage, where you can find a lot of demos on these features. So one feature is, as I already shown in the on the first slides, is edge bundling. Here the idea is that the edges are bundled together, and in fact you also can configure this or customize this so that you can say which of the edges should be bundled. Another feature is integrated labeling. So integrated labeling means that the layout algorithms does the labeling on its own and not as a post-processing step. So when the nodes are placed, also the labels are placed, and it's not done in a simple way where we just place, for example, horizontal labels. This is, of course, also possible, but you can also use radial labels, for example, which also expresses the circular layout very well. Another feature are external edges. So sometimes, and in the coding example, I will show this, sometimes it's good to emphasize some of the edges. So for example, you have a lot of edges inside of this drawing, and then there are a few edges that you would like to draw differently to emphasize them, for example. Then one idea is to draw them outside of the graph, or maybe they have a different meaning than the other edges here. And then you also want to use a different visualization techniques for these edges. And then finally, I also want to mention the node types. So far, the order of the nodes on the circles are determined automatically, but of course, sometimes you also want to customize this. And one possibility is to use node types. Here, the idea is that you give each node basically a color or some kind of type. And the layout algorithm then places the nodes of the same color consecutively on the circle. So here, for example, first the green nodes come, then the red nodes, then the yellow nodes, and then the blue nodes. And this can be also customized and is very helpful to express certain information. Later on in the coding example, I also will give an example for this. And yeah, with this, I already would like to show you the demo of the circular layout. To that end, I will switch to the homepage of yWorks, where you can find a lot of demos, and in particular one about the circular layout. So. And here you can see this example of a graph with this 3 partitions and some other nodes. And what you can do in this demo is that you can just see what kind of features there are, and then you can play around with these features. And I would like to show you some of those that I already mentioned. So let's start with the general layout. And what you can see here is that there's a layout style. And here you can choose different layout styles. Here's, for example, the BCC compact. BCC stands for bi-connected components. So this is done automatically. You can also define a single cycle. This basically means that all nodes are placed on a single cycle. Sometimes this is also very useful. I will later on show also an example of this in the coding example. And so let's go back to the bi-connected components. Different possibility is that you customize the partitions so that you tell the algorithms which partitions should be considered. So let's say that I would like to consider this partition here. So I just introduce a group node. There are different possibilities how you can do this interactively, but here in this demo you can just introduce groups, and this is interpreted then by the algorithms as one partition. So let's say that this should be also a group. And now when I apply this with the custom groups, what you will recognize is that these nodes are then also placed in the circle, and these will be placed in this circle. So let's apply this, and now this happens. And then after that, I could remove these group nodes, and I have a new layout where I have decided how the partitions actually look like. So let's go back to the BCC components. Another possibility is that you define different partition styles. As I said, one possibility is to place the nodes on circles, but it's also possible to place them on disks. So for example, you could use the compact disk layout. Now the nodes are placed on multiple circles per partition, which makes it more compact. So let's go back to the circle. So there are different possibilities. So the organic style does this more an organic layout style, and the disk is less compact than the compact disk. And here, for example, for the edges, you can also decide on how to route these edges. So for example, you can here select automatic, and then the edges, or some of them, are routed around these partitions. And finally, for this demo, I also would like to show the edge bundling. So when I enable this, the interior edges will be bundled. So now this happens, and the interior edges are bundled, reducing the information clutter produced by these edges. Yeah, and this already gives you some idea how the circular layout works. And in the next part of this webinar, I would like to show you how to actually use this in a programming example. Maybe I also should mention, if you want to use this demo on your own, just go to our homepage and you can find there the demos directly, or you can use here this link here. And in the next part, I would like to go to the coding example. And here the idea is that we have a look again at this use case from the computational biology, where it's about this bacterium. And the idea is that we use the data and create, based on the data, two different layouts for the same data. The first part will be about a multi-circle layout, so where we have multiple partitions, which define the wards of the hospitals. And then in the second part, I will show how to use a single circle layout to bring all these partitions together into one circle, but still that you can get some information from this huge amount of data. So the data is given as follows. Basically, it's just a simple JSON file where each node is represented by some record. Namely, a record consists of a name, then the status, so there are patients, but also medical stuff. And then there's also an infection type. So in type D is, for example, this light or this grayish color here. And then we also have the ward of the hospital. So this decides on in which partition the node will be placed. And apart from this information for the nodes, there is also, of course, some information about the edges, which show which nodes are connected. Yeah, and in the first part, I will show how to use this data to get this multi-circle layout. So let's go to the source code. And there are two methods that I will fill with source code, namely the first one multi-circle layout. This is called every time when the graph needs to be layouted, and there we can run our layout algorithms. Later on, when I come to the second part, I can switch this by a simple flag. Of course, you can use some interaction techniques also to do this, but here I just use a simple Boolean flag to say, okay, now I would like to use a different layout type, and then I will show how to do this for the single circle layout, defining the layout settings here in this method. At the beginning, when I execute this method here, the initial layout looks like this. So all nodes are placed on the same node, on the same point, because we have no geometric information about the nodes. So let's change this and let's run the circular layout on the data. So what I first do is that I define a layout, circular layout, and at the same time, I also define the layout data, which we will use to configure this circular layout in greater detail. And what I then do is that I run the layout on the graph using the apply method. And this apply method gets the layout and the layout data. So now I can run this, and what we get is already a view on the graph. And what you see is that there are two large partitions. And as I already said, these partitions are computed automatically. So these are bi-connected components. And this graph actually has only few bi-connected components. So for this graph, it makes really sense to also define these components or these partitions a bit differently, and we can do this based on the data. And this is the next step that I would like to do. I would like to define the partitions of this graph data. So for this, I can use the layout data. First of all, I need to say that I want to use not the automatically determined partitions, but I would like to determine them on my own. And to that end, I can define the layout style to custom groups. Here you can see these different styles: single cycle, BCC compact, and BCC isolated, and custom groups. So I define this here, and then I can also tell the algorithm which node belongs to which group. To that end, I use the layout data and then the custom groups field. And here I use the delegate, and for each node, I decide using a lambda function whether it's to which group it belongs. And the idea is that I return the same object for the nodes that belong to the same group. And this object can be can have any type. And what I will do, I will return just the string of the word to which the person belongs to. And this is stored in the tag. And here we have the word. And this should be already everything that we need. And if I rerun this, we get this layout here where we have these different partitions that we have defined based on the wards of the hospital. So using straight line edges is for this graph in particular introduces a lot of clutter here in this, and we can improve on this by introducing edge bundling. So if you have graphs with a lot of edges, then I would suggest to use edge bundling for these cases here for the circular layout. So what I do is that I define the edge bundling, or I just activate it. Here I use this field edge bundling, then default bundle descriptor, and this default bundle descriptor helps you or does the main part of the work. And for the default bundle descriptor, it's just defined that all edges are used. So actually you can also use other bundle descriptors such that the different edges are bundled or different sets of edges are bundled. So now I activate the default bundle descriptor and I rerun this. One moment, I need to rerun this again. Yeah, now the edges are bundled, and now you can get the information and comprehend the information much easier. If you have a look at this edge bundling, there are also other options like the bundling strength and bundling quality. And for example, for the bundling strength, you can specify how strong the bundling should be. So if I set it to a low value, it's basically that you have straight line edges, and if it's a high value, so its range is between 0 and 1. So if it's almost 1, then it has a very strong bundling. And this already gives you an idea how to use the circular layout for the multi-circle case. And in the next part, I would like to show you how to use it in the single circle case, showing you also different features of the circular layout. So for example, the labeling and external edges. So let's go to the other methods. To that end, I just set this flag here to true. So now not this method is called, but this method is called. And at the beginning, I don't load labels from the data because I want to explain first other things. And then later on, I will set this to true. And then we also get labels for the graph. So again, we need to do the layout part. I can copy this and I also use the same edge bundling, so this is everything is fine with this, but I would like to change the layout style to single cycle. And rerunning this gives you this nice looking image of the graph, and there are a lot of bundles already. But considering the nodes, you can recognize that they appear in a arbitrary order, basically. So sometimes there's a red node, then this grayish node, then this orange node, and so on. And it would be, of course, nice to sort these nodes by their wards, for example. And this is the next step that I would like to do, showing you how to use node types to tell the algorithm how the sequences of these nodes should look like. And this by just categorizing the nodes. So what I do next is I want to define the node types. And we do this in 2 steps. Again, we need to activate this feature, and this feature is activated using the single cycle layout. As I already said, this layout is used as a sub layout by the circular layout. And we need to tell this sub layout that it should use a special node sequencer. So this node sequencer is used to determine the order of nodes on the cycle. And we use the node type aware sequencer. So as the name already says, this takes the node types of the nodes into account. And the next step is that we need to define the node types of the nodes. And this we can do using the node data. So we have here these node types, and we again define them by using a delegate. And this time we have a node again in the lambda function as a parameter, and we need to return which type it has. And again, the idea is that nodes having the same type return the same type or the same object, and we can use any type of object. So again, I can use just the word of the object, and this already defines the node types. So rerunning this example. One moment, I need to rerun it again. One moment, I think I forgot something. No, I didn't. I'm sorry, it's not the word that I would like to type, but the type or the color of the nodes define the infection type. This was a mistake by myself. Then I need to rerun this. And now I get the result that I was looking for. So now the node types correspond to the colors of the nodes. So we have a sequence of orange nodes, a sequence of red nodes, a sequence of blue nodes, and then these grayish nodes. And as you already can see, these gray group of grayish nodes is really large. And then it's often better to improve on the edge bundling. It's often a good idea to split this large group into smaller groups such that it does not cover a whole or a half of a cycle or a 3/4 of a cycle. So what we do in this step is we just split up this really large groups into smaller groups, improving on the edge bundling. And to that end, I introduce a bit more complicated function here. So I say, okay, if the node tag infection is not of type D, so type D is the grayish node color here, then I just return the node tag of the infection. And otherwise, for these grayish nodes, I return also the same tag here, but I combine it with the word of the node, so of the person. So basically what I do, I split these grayish nodes into six partitions, each representing one ward of the hospital. And now this improves on the edge bundling, because now this really large group does not cover anymore basically the whole cycle, but it's split into smaller groups, helping or improving this edge bundling here. So this gives you already a nice view on the graph. You have some more information about the nodes. You can now see at one glance how large these single partitions are. So for example, the orange group or the red group, and you also can easily follow big flows of these edges. Next, I would like to introduce a further technique to express some of the edges, or to emphasize on some of these edges. So what I would like to do is, if two persons have the same infection type and are connected by an edge, I would like to draw these edges not here in the interior of the circle, but in the exterior, using this external edges feature. So, and to that end, I can define the edge routing policy. And so, for example, I could say that it's marked exterior. Marked means that I define these edges on my own. And then what I also now do is that I tell the layout algorithms which of these edges should be shown in the exterior of this circle. I can make this a bit smaller. And next, I get a lambda function that expects an edge as parameter, and then I need to tell whether this belongs to the exterior edges, yes or no. So I basically need only to return true or false. And I do this as follows. I return. I have a look at the source node and at the tag, and here at the infection. And if this is the same infection type as the target node, then I return true and otherwise false. And if I apply this to all of the partitions, I will get the effect that there are many exterior edges also for this Grace node type or infection type, which blows a bit up the layout. I can show this. And this is just the reason because the data is like this. So it's, and in that case, it pays off to say, okay, we don't want to do this for all of our data, but only for the smaller partitions like the red and orange and the blue ones. And to that end, I can introduce a further condition, and I just say, okay, and the infection type should not be type D. I need to rerun this. Yeah, and now what you get for as a result is that, for example, here these red edges are placed outside of the circle. Zoom in here. And these edges mean that they are connected between two persons having the same infection type. So, and finally, I would like to show how to use labels for this example. To that end, I just load the labels. And when you have a look at these nodes here, the labels are placed on top of the nodes. In many cases, this is completely okay, but in our case, it would be nice to have these icons of these persons and to place the labels besides, and in a radius fashion pointing to the center of the circle. And to that end, we can define the node labeling policy and say that this should be ray-like. And in order to activate this, we also need to tell the algorithm that it should use the integrated node labeling. So if I restart this, the labels are placed around this circle in a radial fashion. I can zoom in, and here I just use the names of the persons as a label. Here you see maybe another problem, namely that the edges are hidden by the labels, but we can improve on this very easily by just increasing this radius of these external edges. So for this, we can say that we use the exterior layout, edge layout descriptor, and here the circle distance, and let's say we set it to 100 pixels. And now what happens is that these edges are drawn outside of this radius of the labels, and getting their own layer basically with 100 pixels apart from the nodes, and they are not covered anymore on these circular parts of the edges. Yeah, and this already concludes the part of the or the second part of the coding example, and you have learned how to apply the circular layout on a large data set using edge bundling and also other techniques like the radial node labeling and the exterior edges. So let's go back to the slides. And with this, I already want to conclude the webinar. In this webinar, you have seen how the circular layout works. You have learned about this approach that is split into two parts, and you've seen that the circular layout uses different other standalone layouters of the yFiles library as sub-layouters. And the idea is that you can also configure these sub-layouters for your purposes. And for example, in order to visualize social networks from computational biology, and also networks for computer networks, but of course there are many different other use cases you can think of. Maybe a small sneak peek, preview on the next release. There you will also get the possibility to lay out star structures. So here the idea is that you have a star structure like this. Then you can explicitly say that this should be done in a certain way. And if this star structure also occurs on one of the circles, this will be also done on this circle here. Yeah, and this will be published in the next release, in the next main release. And yeah, with this, I would like to conclude the webinar. And as I already said, now there's a Q&A session, and I now will have a look at the chat and see what your questions are, and I then will try to answer them. So okay, the first question is, I just read them out loudly. When you say the library processes automatically, you mean the position of the nodes in the graph. So I mean, I always have to explicitly tell you what nodes to connect, right? And yeah, that's right. You always need to define the structure of your input graph. So the layout algorithm does not know how the connections between the nodes is. This is a semantic information and depends highly on your data. But if you have this information so that you know how these nodes are connected to each other, then the layout algorithms uses this information to place your nodes in the plane and tries, for example, to minimize the number of crossings between edges. And there are many different optimization criteria that you can do. The next question is about the single cycle layout. So the question is whether or how is the radius determined of the single cycle layout. And there are basically two answers, namely that either it is determined automatically, or you can manually set this, so you can customize this, and you can decide on this, of course. So you can set a property that it should be determined automatically. In that case, the radius is chosen such that it is minimal, but still the minimal node distances are taken into account and no nodes overlap. So this is when you do this automatically, and the different other possibility is that you define this radius on your own. Then there's also another question. So I have a large graph that I would like to lay out with a circular layout. Can I influence the compactness of the layout? Yeah, there are many, or there are different possibilities to do this. One possibility is, of course, to define the minimum node distances. So if you define them very large, you will get an uncompact graph. If you define them small, the nodes will shift together, and you get a more compact graph. But the layout algorithm, especially the sub-layout algorithms of the circular layout, allow you to further tweak the compactness by setting, for example, a compactness factor, or the balloon layout allows you to also define these wedges. So if you define large wedges, the layout can become more compact. The other possibility is that yeah, you define or you use different partition styles. So for example, if you really want a compact layout, what you can do is you can use the compact disk layout for the partitions, which basically then means that the partitions become small, and then the remaining layout can also become more compact. I hope this answers the question. And the next question, do I always need to define the edges to be routed outside of a partition on my own? So the question is, do I need to define these exterior edges as I've done in the coding example on my own? And the answer is, if you want to, you can do this, as you have seen in the coding example. But there are also possibilities to determine this automatically. And in this case, the algorithm tries to minimize the number of crossings between the edges, and then decides on this information which of the edges go through the interior of a circle, and which of the edges go around the circle. Yeah. Okay, I think that were all questions. Yeah. Yeah, and with this, I would like to wrap up this webinar. I thank you very much for the attention, and I hope that that you also will attend the next webinar, which will be about the edge routing, our edge routing techniques. And with this, I would like to end this webinar. Thank you, and happy diagram.